Alright, today we have the chronograph. We have a list of arrows here. We have one that is essentially a stock arrow. I have this one right here set up with this monstrously heavy 300 something grain brass insert and a bunch of other weights in between. So what we're going to do, we're going to weigh these up, run them through the cheap shot, chronograph them, and see if we get any interesting results. Alright, while I'm busy doing that, I want to show you something else. I got this idea from Pistol Crossbow Fan to take a bow fishing setup and put it on the crossbow. I haven't figured out a mounting system yet. I didn't want to spend the $300 to get a basic mount, but I did hear a proof of concept with a water jug. Worked out great. Give it a try. Yeah, that was a little chocolate bunny on the jug there. Yeah, never stood a chance. But I'm still doing that. I shot some cans. That's pretty fun. I'll just get done already. Our lightest first, 246. $210, $271, $207, $286. Now you may notice I'm using a very heavy double serving Kevlar string there. That might be part of the reason some of these results are slow. And a 385. My last one broke and I had to make a new one. 186. 380. 187. 10. 196. 416. 176. And lastly, the monstrously heavy 624. That one had some kick. Alright, now we gotta go derive our data. So this is our bow in question, is the cheap shot. And we have the values that we're going to be using to get all of our other numbers. And here is the number we need to derive from those. Our kinetic energy and momentum. And to make sure Canada and Europe can fall asleep too to this data, we'll convert it to metric. Alright, we'll just go ahead and enter our data here and get to cracking. Now we got to get our formula for energy. We take our grains, divide that by 7,000, turns it into pounds, multiply that by our velocity, and then the velocity gets multiplied again because physics, and we divide that by half, and then we let it know that we did all this measurements on Earth, and so we have to divide everything by 32, as in gravity causes things to fall at 32 feet per second squared. And get rid of some decimal places, and there we go. We got a nice little 24 foot-pounds of energy with our lightest projectile. And for the slug calculator, a similar thing, only that is velocity times mass. And now we just enter in our conversions for the metric, and then we derive our data. Oh, look at that. Beautiful. Now one other thing we need to look at is the efficiency of the bow, because you have to figure that our energy output changed as we changed the weight. Now our theoretical energy potential is going to be the peak draw weight multiplied by the draw length And because the draw force curve is going to be roughly the approximation of a triangle, we divide that by half and convert that into foot-pounds, which gives us about 40 foot-pounds of potential energy. So let's convert that to metric real quick. So if we take our actual result and divide it by our potential energy, we can get our efficiency number. So we'll just go ahead and do that quick. Alright, now let's derive this out. Just under 60%. Oh, oops. Forgot to reference the number properly. My bad. Let's fix that quick. $sign for absolute, because why not? Alright, there we go. And we can see here that with the exception of that short bolt, for the most part, as we increase the weight, our efficiency goes up and our kinetic energy and momentum also go up, which isn't a huge surprise. If you think of it as if we dry fired it, we end up with 40 foot-pounds of energy getting turned into vibrations and heat and broken strings, and then as you add weight, you give that energy somewhere to go. And that's where your conventional wisdom that recurve bows generally do better with heavy arrows. I don't know if this is true of compound bows or not. If someone's got a compound bow and wants to give this a try, go for it. I'd like to see the results. Anyway, I hope a video that's half day to dump isn't too tedious. In any case, thanks for watching.
Yes, Kitty. Again, there's so much waiting. The weight has to be going one way to wait. Oh, oh. Ah. Ah. Aw.
Probably get that little camera out.
Although that's what's making it so entertaining. Well,
It's also distracting them from using it as
oh.
what it's for.
Well, yes and no.